So at this point, what I would like to do, okay, is to replace this hyperbolic square x, hyperbolic cosine y square y um with using this formula or using this identity. Okay, so that is, I would like to have hyperbolic cosine square y, okay, equals or equal to 1 plus hyperbolic sine um, square y. Okay? So, consistent siya dito sa ano natin, sa identity na to. Okay, so again, replace it, I would like to replace this one with this one. Okay, so I'll have um, cosine of z square, okay, or the magnitude of cosine square z square is cosine x, okay, cosine x times 1 plus hyperbolic sine square y plus sine square x times hyperbolic sine square y. Okay? And then we'll multiply out this term. Okay, i-multiply out natin siya to produce two terms, cosine x plus cosine, sorry, this is cosine square, no? So cosine square x, okay? So that's the first product, and then the second product is cosine square x times hyperbolic sine square y. And then the third term, this one, that's sine square x sine square x and then hyperbolic sine square y. Okay? Now observe the last two terms of the result, okay? Um that they have the common factor hyperbolic sine square y. So we can actually factor them out, okay? So writing the first term first, and then the first factor is what is left out after we factor out hyperbolic sine square y. So yung factor na yon is cosine square x plus sine square x. And then, ito nga, yung i-factor out natin, hyperbolic sine square y. Okay? So, ayan. Now, notice that cosine square x and sine square x was established here. And that we know for a fact, again, using the Pythagorean identity, okay, we know for a fact that this is equal to 1. Okay? And therefore, that establishes that the expression of the magnitude of cosine z square, okay, is equal to cosine square x plus hyperbolic sine square y, which is what is required for us to establish. And this is formula 7a. Okay? So, there. Ayun, yan yung formula 7a natin. Okay? Now, I would like you to, as an exercise again, I would like you to work on trying to verify formula 7b. Okay, so try to verify this 6b, and then try to verify also formula 7b. Also, just a point of an exercise again. Please try to prove this please try to verify this identity. Okay, so that you would be able to convince yourself that indeed this identity holds true. Okay, so that's for example 8. Now let's proceed to example 9. Okay, so let us try to solve these equations. Okay. Alright, so let us try to work on letter A first. Okay, which asked us to solve cosine of z equals 5. Okay. Now, it might surprise you that a problem as simple as this one would actually have no real solutions. Okay, but that is really possible. In fact, in this case, this problem does not have really a real solution, which we will see later on. Okay, so to start working on this one, actually we have two options of working on this one. The first one is what I would demonstrate. Okay, and by using the exponential equivalent of cosine of z. And the second one is by the use of 6a, or formula 6a, which you have established earlier. Okay? So, let us use the exponential equivalent, okay, and see and write cosine of z as e raised to iz plus e raised to negative iz divided by 2, which is equal to 5. Okay? Now let's eliminate the fractions here by multiplying the both sides of the equation by 2. So we will have e raised to I z plus e raised to negative I z equals 10. Or basically, that is minus 10. Okay? That I'll make it minus 10 equals 0. That is, I would transpose 10 to the left side. Okay? Now, let us multiply this equation, the resulting equation by e raised to iz, okay, which would yield, okay, this would yield now the equation, um, this is e raised to I times e raised to I. Okay, so that's basically, you're multiplying the same number. Okay, so that multiplying a number with itself squares it. Okay, so that means the product e raised to iz times e raised to iz is e raised to 2iz, or basically that's e raised to iz squared, and then using the property of exponents, we can rewrite this into this. Okay, and then e raised to negative iz times e raised to negative iz is equal to 1, because basically you're multiplying a number to its reciprocal. Okay, take note that these two are, aside from they are conjugates, in the real number realm, these are reciprocals. Okay, but in the complex number realm, they are conjugates. Okay, and the product, when you multiply the conjugate of two complex numbers, the result is their magnitude. Okay, the result would be their magnitude, and the magnitude of e raised to negative iz and also of e raised to iz is basically 1. Okay, so therefore the product of this is 1. Okay, so this becomes plus 1. Okay, and then minus 10 e raised to iz equal 0. Okay, now let's rearrange this equation. Let's rewrite this as e raised to 2 iz minus 10 e raised to iz plus 1 equals 0. And observe that this equation is actually a quadratic equation. Okay, this is quadratic in terms of e raised to iz. For example, if you actually let m equals e raised to iz, okay, this equation becomes m squared. Okay, this equation becomes m squared minus 10m plus 1 equals 0, which now can be solved using the methods we use to solve quadratic equations. Okay, but you have a calculator for this one. So let us just simply use your calculator, okay, and see that the roots, okay, for your quadratic equation, okay, are this. Okay. I use a calculator for this one, but unfortunately I don't have my online or my computer my emulator, okay, for Casio calculator. I have yet to pay for the license. Okay, so um I'll just use my on-hand calculator and write the results here. But you can verify it. Okay. I used the quadratic equation solver of my calculator, and I reported because the results are contains long decimal numbers. Okay, I reported them using 5 decimal digits, 5 decimal places, so that I can protect at least the 3. Okay, to be correct. I can be sure that at least 3 of the decimal places are correct. Okay, so these are the two roots. Now, take note that m, okay, is equal to this one. Okay, so therefore, we can have e raised to ij, okay, equals 0.10102, okay, and on the other half, the other solution is ij equals 9.89 9.89898. Okay, now again, we take note that z, okay, that z is x plus iy. Okay, we take note that z is equal to x plus iy. Now we replace z here with this one, okay, and come up with e raised to I times x plus iy. Okay, I'll just do it here so that no. Okay, so we have e raised to I z, and then we will replace z with this one. So we will have e raised to I times x plus iy. So that should be, or that should become e raised to ix. This is I times I, so that's I squared. That's -1. So this that becomes minus y. Okay, or basically we will have e raised to negative y plus ix, or equivalently, okay, this is e raised to negative y, okay, times e raised to ix. Okay, so we will use this to replace e raised to iz. Okay, so for the first half of the solution, we will have e raised to negative y times e raised to ix equals 0.10102. Okay, so how do we try to work on this one? Okay, take note that this is a real number. 0.10102 is a real number. Okay, to make this a complex number, there should be a an exponential that is multiplied here. Something like e raised to I theta. Okay, but the mere fact, so that we can equate the two. Okay, this is the real part. Okay, the real part of your number, okay, or the magnitude of your number. So it would be equal to this one, which is a real number. Okay, and then the exponential part. Okay, but the thing is that we cannot see the exponential part, basically because in this case, your your exponential is actually equal to 1. This exponential is equal to 1. Okay, and for you to be able to make that 1, then it must mean that the angle here should be 0, because e raised to 0 equals 1. Okay, equals 1. So that this would imply, therefore, that we have e raised to negative y equals 0.10102. Okay, and then the other half is that x here equals 0. Okay, again, for you to be able to not see, or for the fact that you cannot have an exponential here, okay, means that that exponential is equal to 1. And for you to make that exponential equal to 1, then the exponent must be 0. So in that case, this is e raised to ix. Okay, x here must be equal to 0. Okay, but basically, since we're talking about x here being the angle, okay, of the argument, okay, for this exponential, x equals 0 is actually a principal argument. Okay, as we have established on the previous lesson, that the argument, or you can find the other the other parts, okay, or the other numbers, okay, associated with e raised to ix by adding multiples of 2 pi, okay, multiples of 2 pi to the principal argument. So we will have here plus or minus 2 pi n for n equals 0, 1, 2, and so on. Okay, so that would be the value of your x. Okay, while um, to find the value of y, okay, to find the value of y, we will have we will apply natural logarithm on both sides. Okay, so this should give us negative y times the natural logarithm of e equals 0.10102. Okay, and then we can solve y here. Okay, sorry. It should be the natural logarithm. Okay, it should be the natural logarithm of um, 0.10102. Okay, and therefore y is negative of the natural logarithm of 0.10102, okay, which is when we approximate it using your calculator, okay, when we approximate the value of that number using your calculator, that is verify with your own calculators. This is 2.292 in 3 decimal places. Okay, so that would be your y. Okay, and then this is your x. Okay, so that we take note that in this half of the solution, we have two solutions, so this is the first half of your solution. Okay, we take note that z, which is again x plus iy, okay, is equal to plus or minus 2 pi n. That's the value of your x. Okay, plus 2.29 2.292i. This is for n equals 0, 1, 2, and so on. So these are the solutions for your z. Okay, and that's just the first half. Okay, now for the second half, we deal with this one. Okay, so again, we say that e raised to iz equals 9.89 8998. Okay, and take note that e raised to e raised to iz is e raised to negative y times e raised to ix, okay, which is equal to 9.89898. And again, using the same argument as I did on the first solution, we can establish that e raised to negative y equals 9.89898, and then x equals 0. Okay? It's using the same reasoning that I did before. Okay, and then again, since this x is an argument, okay, for your exponential, okay, we see that we need to add multiples of 2 pi to that one, okay, to include all those ambiguous numbers, okay, that that results from using the exponential form. Okay, so we'll add 2 pi n, okay, for n equals 0, for n equals 0, 1, 2, and so on. Okay? Now, we need to solve for y here, okay, which can be solved by computing negative of the natural logarithm of 9.89898, okay, which this formula was obtained from the previous solution, okay, which gives you negative 2.292, which is basically the negative counterpart of this number. Okay? So actually, both of the solutions can be combined into one compact form. Okay? Basically, both of their angles or both of their arguments occur on the same numbers or occur on the same values of x. So they have the same values of argument. Both of the solutions have the same values of the argument. And the real and y here is basically just a positive and a negative of the same number. Okay, so therefore, we can write now z as x plus iy, which is equal to x is plus or minus 2 pi n. Okay, so I since the principal value is or the principal argument is 0, I need not to write it here. Okay, and then um, plus or minus the plus originating from the first half of the solution of your quadratic equation, while the negative originates from the second half. Okay, so this one and this one. So this is plus or minus 2.292 I. Okay, which is defined for n equals 0, 1, 2, and so on. Okay, so again, as I mentioned at the start of this problem, that this problem or that equation does not really have um, real solutions. Okay, if you take note that if you set n equals 0, which is the principal value of z, okay, um, z becomes plus or minus 2.292i, which is an imaginary number. So, and that becomes more complex as you actually increase n because you still have this part. Okay, so as I said, this problem or this equation, the original equation, does not have a real solution. All of its solutions are complex. Okay, so this one is the solution. Okay, now I leave again example 9b and 9c. Okay, into your own as your own exercises to be able to solve them. So these are opportunities for you to practice on how to get on how to solve this z. Okay, but basically the principle and the manner by which you can solve them is the same as how we were able to do it here. Okay, so you can base your solutions on this method that I have just demonstrated. Okay. Okay. Now, even though that we are in the complex domain, take note that the identities that you were able to establish using real numbers, okay, actually hold true also for complex numbers. For example, in the formula 9 for cosine and sine establishes the formula or the identities for sum of two complex numbers, the cosine of the sum of two complex numbers, okay, and the sine of the sum of the two complex numbers. Okay, they are basically the same as your sum of angles formula. Okay, ito yung these are the analogs in the these are the analogs of these formulas in the complex domain. Ito yung pinakita ko sa inyo kanina. Okay, yung kung saan natin nakuha yung cosine of alpha plus or minus beta. Okay, this is in real in terms of real numbers. This is cosine of alpha times cosine of beta minus plus, okay, sine of alpha, sine of beta. Okay? So this is the identity that you have established in the real number domain. Okay? And this is the analog, okay, or this is the similar identity that holds true for numbers in complex domain. Okay? So as you can see, pareho lang naman sila. Okay? Even in the sine function, sine of alpha plus or minus beta is sine alpha cosine beta plus minus cosine alpha sine beta. Okay? So they're similar. I'm saying that they're not the same because you're talking about real numbers here. Okay, on this side. And on this side, you're talking about complex numbers here. So the forms are basically the same. The best that I can describe them is that they are similar or they are analogs of each other. Okay, and analogs. Okay. Um, but they're not necessarily the same, or they don't mean the same thing. Okay, because for one thing, on this side, this is true for complex domain. Okay, and while this one on this side, this is true for real number domain. Okay, so I just the best that I can describe them is that they are just similar. Okay, even the Pythagorean identity. Okay, that cosine square x plus sine square x is equal to 1 has a similar property or a similar identity with that of the um, or within the complex number domain. Okay. Um, in terms of hyperbolic functions, okay. In terms of hyperbolic functions, we have in terms of complex numbers. Take note here that z is now a complex number. Okay. So z here is a complex number, again equal to x plus iy. So this is hyperbolic cosine of z equals 1/2 of e raised to z plus e raised to negative z. Okay. The real number formula for that is a hyperbolic cosine of x equals 1/2 um, 1/2 times e raised to x plus e raised to negative x e raised to negative x. Okay. And then similarly for hyperbolic sine of x, this is 1/2 um, e raised to x minus e raised to negative x, where x are all real numbers. In this case, you have you have similar formulas for hyperbolic functions in complex domain. Okay. Similarly, the other hyperbolic functions, okay, are also defined, okay, um, with with the similar definitions, okay, from their trigonometric counterpart, okay, and also they have the same they have the same descriptions, okay, when they whether they are on the real domain or on the complex domain. Okay, so there. Now, how is the complex trigonometric and complex hyperbolic functions related? Okay, so formula 11 will establish the similarity. And actually, we have already we actually have uh, established these two formulas earlier. Okay, we were able to find that cosine of we only have found cosine of iy, which is equal to hyperbolic cosine of y. Okay, and sine of iy is equal to hyperbolic sine of I hyperbolic sine of y. Okay? Now, we'll just replace values. Okay? Instead of using y, we'll replace it with z. And z here is basically the general complex number that you have, x plus iy. And still, it would hold true. These formulas would still hold true. Okay? Although we initially established these formulas uh, for the purpose of determining what is cosine of iy, and we are thinking that iy is just a purely imaginary number. Okay, that also holds true. The same formulas can also hold true for your z being a complex number. Okay, now in a similar manner, um, if we now have to relate complex hyperbolic functions to its trigonometric counterpart, we have the following. Okay, so we see that hyperbolic cosine of ij is equal to cosine of z, and hyperbolic sine of ij is equal to I sine of z. Okay? So we have here the case of unrelated of real functions, okay, that have related complex analogs. Okay, so again, in the real number domain, these two doesn't have any relationship between them at all. Okay? The only thing that holds them together is how they are named. Okay? And again, the reasoning for the naming is that even though hyperbolic functions are complex numbers, are exponential functions, or are fundamentally complex exponential functions, they actually have properties that are similar to trigonometric functions. And after that, they don't have any relationship at all. Okay? This time, in the complex number domain, these two can actually be related to each other. Okay? By having a complex argument, um, convert it to another form of the function. For example, if you're starting with a hyperbolic function and you make the argument complex, that would be converted to um, a real trigonometric function. Okay, and in the conversely, if you have a complex argument for um, trigonometric function, that would be converted to a real hyperbolic function. Okay, so one thing that I actually forgot to demonstrate to you is actually how to use the formula 6a. Okay, so again, formula 6a is basically cosine of z, okay, which is cosine of x times hyperbolic cosine of y, okay, minus um, I times sine of x times hyperbolic sine of y. Okay? So, basically, if we have, say for example, z equals 3 plus 4i, and then we are asked to evaluate the value of the cosine of this number, okay, we will basically have um, cosine of 3 plus 4i equals cosine of 3. Okay, and this is in radians, okay? So remember that at this point, all of the arguments, okay, that these trigonometric functions carry are all in radians. Okay, so cosine of 3 here means cosine of 3 radians. For the case of hyperbolic functions, it doesn't matter whether y is a degree or a radian. Okay, it doesn't matter. Okay, again, the argument for hyperbolic cosine can actually take any units. Okay, not just angles, because basically these in applications they don't generally refer to angular measurements. They actually are exponents of an exponential function, so they can actually carry on any quantity, not just angles. Okay. So, but in the case of trigonometric functions, the angles are radians. So, cosine of 3 times hyperbolic cosine of 4. Okay. Let us be consistent. If we will place a parenthesis here, we will have to place also parenthesis here. If you're not placing parenthesis, it's you have to do both. Okay. So, just be consistent with your writing. So hyperbolic cosine of 3 times cosine of 3 times hyperbolic cosine of 4 minus I times sine of 3, okay, times hyperbolic sine of 4. And then we'll evaluate this value. Okay? So I will use a calculator for this one. Okay? So after calculating these values or these expressions on my calculator, I found that this first term, okay, this product is actually equal to negative 27.0349, reporting the results to 4 decimal places. Okay, and then this product is equal to 3.8511, and then we multiply it by I. Okay, so this is what you should verify this with your own calculations. Okay, so that is your cosine of 3 plus 4I. Okay, so that ends section 1.4, okay, in which we discuss here um, uh, evaluating trigonometric and hyperbolic functions with complex arguments.